In the last class, we were trying to discuss about unconsolidated undrained test, which is in simple terms also called as undrained test or UU test. Okay, so we started talking about how do we conduct the test on your cylindrical soil sample in the case of your UU test. We said in both the stages of the loading, you are not going to be allowing anything called as water to get drained out of the soil sample. So while the first stage of loading is applied, that means when you are applying the confining pressure on the soil sample, the water is not allowed to get drained. So in the sense, the soil is said to be unconsolidated. And even in during the application of your deviatoric test, that is the second stage of loading, you are not allowing the water to get drained. So the soil is said to be in undrained state only. So that's the reason why we call that particular test to be UU test, where U refers to unconsolidated and the second U refers to undrained. Okay. And we went on saying that, okay, if I take my soil sample from the field, there is a possibility that some residual pore water pressures would still remain in that soil sample. I'll just try to talk about that in the next couple of slides. So that residual pore water pressure, whatever is existing in the soil sample, will still remain in the soil sample. Why is it remaining in the soil sample? Because you release the load. When you have released the load, there will be some pore water pressures which will still remain in the soil sample, and that pore water pressures are rather, in fact, not to be called as your positive pore water pressures. Rather, that is to be called as your negative pore water pressure. Why is that negative pore water pressure coming into picture? Because earlier, whatever was the load that was getting developed on that soil sample was released, because of which a slight amount of elastic recovery might have taken place, slight increase in volume might have taken place in that particular soil. As there is a slight increase in volume of the soil, so that subsequent pore water pressures which that soil has been experiencing when it was there in the field, so that pore water pressure will no more remain in the soil. Rather, now there is some other pore water pressure what the soil will contain in it, and which is called as your residual pore water pressure. And that residual pore water pressure is more specifically called as your negative pore water pressure. Because why is that negative pore water pressure coming into picture? Even in the case of your over consolidated soils also, when we said as the soil is over consolidated or dense, so when the shearing is happening, the volume is increasing. Due to the increase in volume, the subsequent pore water pressures building up in the soil are no more going to be positive pore water pressures. Rather, they are called as your negative pore water pressures. Here also the similar phenomena. Once the load was removed from the soil, when it was taken out from the ground where it was, from whatever depth you are taking out the soil sample in undisturbed state. So once that soil sample is taken out of the ground, the load which was earlier acting on that soil sample is now released, because of which a slight increase in volume might have happened. And because of that slight increase in volume of the soil, your so-called pore water pressures which were existing earlier now gets changed to negative pore water pressures. So, and that pore water pressure, what exists and remains in the soil sample, is what is called as your residual pore water pressure. That is not going to become zero, but however, slight amount of negative pore water pressure should be existing in that particular soil sample. Yeah, this is all what we have talked about. So when hydrostatic cell pressure, that is nothing but when confining pressure is applied on the soil sample, so there will be an increase in pore water pressure in that soil sample, and that increase in pore water pressure, whatever is getting developed in the soil sample, because of the applied cell pressure or confining pressure, we said we will be writing it as B into delta sigma 3, where B is nothing but we call it as your Skempton's pore water pressure parameter. And we went on to say that your B parameter, whatever we are trying to talk about, is basically a function of your degree of saturation in the soil. Earlier, already we have talked about this particular case. So delta UC is nothing but increase in the pore water pressure due to the application of your cell pressure on the soil sample, and delta sigma 3 indicates your increase in cell pressure. How much was that corresponding cell pressure applied on the soil sample? Because of which, how much was your Skempton's pore water pressure parameter coming into picture, B parameter, which we call it as, where that B is going to be equal to 1 when your soil is fully saturated, and the B value is going to be less than 1 when the soil is partially saturated. That is already what we have talked in our last class. In similar lines, when your axial loading is applied, which is trying to cause the shearing in the soil sample, that axial load is what we call it as your deviatoric stress. So when the deviatoric stress is applied, the shearing is happening in the soil sample. And in the process of shearing the soil sample, we said apart from the existing pore water pressures in the soil sample, due to that additional deviatoric stress, some more excess pore water pressures are getting developed or built in your soil sample. So that excess pore water pressures, what are additionally getting developed because of the applied deviatoric stress, is what we can calculate in terms of your another parameter. So that increase in pore water pressure, whatever we are coming across, delta UD, because of your applied deviatoric stress. In the last class, I hope I was trying to use a simple representation A into delta sigma D, but now I am just trying to give a slight difference. Okay, please do understand there is a small change in the representation. I am indicating it as A dash into delta sigma D. What is this A dash means? I'll just try to represent. That A dash is what I am calling it as once again your Skempton's pore water pressure parameter A dash. Okay, and that so-called Skempton pore water pressure parameter A dash is what I'll be writing in my subsequent steps. I'll be showing you. Okay, so when cell pressure is applied, this much amount of confining, this much amount of increment in pore water pressure is coming into picture. Excess pore water pressure, additionally, how much is getting developed because of the applied confining pressure is what we understand as delta UC. And because of the applied deviatoric stress, how much additional increment in pore water pressure we are coming across is what we are representing it as A dash into delta sigma D. And total pore water pressure, whatever increment that you are coming across at any stage of your UU test, is because of your applied confining pressure as well as because of the increment in deviatoric stress that is coming on your soil sample. Okay, so because of your applied deviatoric stress, because of your applied confining pressure and because of the applied deviatoric stress, some increment in pore water pressure you are coming across with, and that total increment in pore water pressure contribution is coming into picture because of this term as well as because of this term. Okay, so total pore water pressure, total excess pore water pressure, what is getting developed in the soil sample is because of the increment in pore water pressure due to the applied confining pressure and increment in pore water pressure due to the applied deviatoric stress. And increment in pore water pressure due to the applied confining pressure on the soil sample is what we have presented as B into delta sigma 3. So this term is what I am replacing it as B into delta sigma 3, whereas this term is what I am replacing it as A dash into delta sigma 3. And this A dash is what I am trying to rewrite it as A into B. Okay, to be more specific, this capital A stands for your Skempton's pore water pressure parameter A, and capital B stands for Skempton's pore water pressure parameter B. Okay, so this A dash is what we are in simple terms writing it as A into B. Okay, so this total increment in pore water pressure is what we can write it as B into, because in these two terms, in first and second term, you have your B term common, okay, as like what we see here from this particular expression. So B is common, so that B term, if it is taken common out, then what I'll have inside the bracket is delta sigma 3 plus A into delta sigma 1 minus delta sigma 3. What is this delta sigma 1 minus delta sigma 3 means? It's nothing but your applied deviatoric stress on that particular soil sample. Okay, so this expression, whatever we have, is nothing but we call it as your Skempton's pore water pressure equation. Okay, so this particular expression, whatever we are trying to look at, is nothing but we call it as Skempton's pore water pressure parameters equation. And if I know your A parameter and B parameter, Skempton's pore water pressure parameters A and B values, and if I know how much is the amount of confining pressure that is applied on the soil sample, and if I know how much was the corresponding deviatoric stress that is getting applied on the soil sample, then at any stage of your shearing, I can try to calculate how much is that corresponding increment in pore water pressure that we are going to be coming across with in your soil sample. Now, if we just try to understand, as I told you, like your Skempton's B parameter is basically a function of your degree of saturation, which we have already talked about earlier. And we have also said your Skempton's pore water pressure parameter A is a function of your ore consolidation ratio, which we have already talked about. Now, if I'm just trying to look at a graph which is plotted between the degree of saturation data and your B parameter. How is your B parameter varying? Depending on the degree of saturation value. In case if the degree of saturation value is 0, the corresponding B parameter what we are looking at is also nothing but 0, because the degree of saturation, if it is 0, then your Skempton pore water pressure parameter is nothing but it is equal to 0. B parameter is nothing but equal to 0. Why is it 0? Because if soil is not at all having any degree of saturation, it means it is a dry soil. In dry soil, you don't talk anything about your excess pore water pressures building up in your soil sample. That's the reason why your Skempton's pore water pressure parameter B is nothing but it is equal to 0. Okay. So with increase in degree of saturation, what we see is that your Skempton pore water pressure parameter B is also going to be increasing like this, and your B parameter becomes equal to 1 for the degree of saturation in the soil to be equal to 100%, which we have already talked about. So in the case of your fully saturated soil, your B parameter is nothing but it is equal to 1. Okay. Now coming to the case of your A parameter, if we are trying to look at the condition of your A parameter, that is your Skempton pore water pressure parameter, which is said to be a function of your ore consolidation ratio. How do we define ore consolidation ratio? We know that ore consolidation ratio is defined as your maximum pass pressure to that of your current effective stress. What is your maximum pass pressure? I can write it as PC dash by current effective stress, maybe something sigma naught dash, or maybe whatever notation you are using. This is your pass pressure. This is your current effective stress. Okay. So at present, how much is the effective stress getting developed in the soil sample? In the past, what was the maximum stress that your soil sample has experienced? So once that data is known, I can calculate what is the ore consolidation ratio of that particular soil. So depending on the ore consolidation ratio of the soil, your so-called A parameter, Skempton's pore water pressure parameter, okay, at the failure of the soil sample, if I want to write down, so people do also write it as, instead of writing it as A, at the failure of the soil sample, if I want to define, so at failure, that so-called Skempton pore water pressure parameter A is what I can also write it as AF. F there indicates it's the failure, at the failure of the soil sample. What was your Skempton's pore water pressure parameter A? Now, if I just try to understand, earlier when we were trying to discuss, let's say for saturated soil, if I'm just trying to look at, in the case of your saturated soil, let me just go on to understand the expression what we have represented. Delta UD is nothing but B into A into delta sigma 1 minus delta sigma 3, where delta sigma 1 minus delta sigma 3 is nothing but we call it as your deviatoric stress. Because of that applied deviatoric stress, correspondingly, how much is your increment in pore water pressure is what I am just trying to look at. Once I say the soil is fully saturated, this parameter B is nothing but it is equal to 1. And at failure of the soil sample, if I just want to understand, then I can say that increment in pore water pressure because of the applied deviatoric stress at the failure for some corresponding applied deviatoric stress on the soil sample, what is the corresponding increment in your pore water pressure. Okay, so that is what I am writing it here, which is equal to A at failure is what I am trying to write down, because B is equal to 1. I am referring to the case of a saturated soil. So this is nothing but delta sigma 1 minus delta sigma 3 at the failure of the soil sample. So at the failure of the soil sample, how much was the corresponding deviatoric stress what is applied? So based on that, I can go on to write down what is your parameter A at the failure of the soil sample. Okay, this is something what we can go on to write down. So in case if I know your Skempton pore water pressure parameters, I can go on to calculate how much is the increment in pore water pressure existing in the soil sample at any stage of your shearing in the soil. It need not be only at the failure. So at any stage of your shearing, I can go on to calculate how much is the corresponding increment in pore water pressure that you are coming across with in the soil sample. Let me just try to see by plotting a graph between over consolidation ratio indicated on the horizontal axis and your A parameter, that is your Skempton pore water pressure parameter. Maybe at failure or in simple terms, if you want to indicate, you can represent it like this. What you will see is your curve, what you will be getting would go like this. So what is it indicating means maybe maximum your AF value what you will be coming across at the failure of the soil sample. This parameter can approximately go somewhere around 0 to 0.65. And let's say on the horizontal axis, you have your over consolidation ratio data indicated. Let's say on a logarithmic scale. So 1, 10, maybe 100, 1000 and so on. Accordingly, we'll be trying to plot a graph. Now, what we need to understand from this particular graph which we have plotted is, okay, this AF value, whatever we understand from this, higher the over consolidation ratio of the soil, your AF value can also become negative. Okay, so in soils which are said to be highly over consolidated, I repeat, for the soils which are said to be highly over consolidated, your AF value can also be even negative. Okay, so your AF value is also going to be negative in case if the soil is said to be highly over consolidated. So AF is even less than 0 in the case of highly over consolidated soils. So less than 0 in the sense AF value can also be even negative in the case of the soils which are said to be highly over consolidated. Okay. So next, moving on with your state of stress, what your soil sample is subjected to in the case of your UU test, if you want to understand. So total stress is nothing but equal to your neutral stress or pore water pressure and plus effective stress. So immediately after sampling in the sense, once we take the soil sample out of the ground, the amount of stress acting in the vertical direction and on the in the horizontal direction on the soil sample is 0, because once the soil is removed from the ground at undisturbed state, the soil sample is not subjected to any stresses externally. Okay, there is no state of stress acting on the soil sample. But however, as we have discussed, we are going to come across with some negative residual pore water pressures which are getting developed in your soil sample. And what happens to my effective stresses that are getting developed in the soil sample means effective stress are nothing but total stress minus pore water pressure. So 0 minus your residual pore water pressure is nothing but it is equal to your effective stress, both in the vertical direction as well as in the horizontal direction. Now, immediately after the application of your cell pressure, that is your first stage of loading, then what is going to happen is you are not allowing any drainage to happen through your soil sample after the application of the cell pressure. So because of that applied cell pressure, there is an additional increment in pore water pressure, and that additional increment in pore water pressure is because of your confining pressure what you have applied. And in case if the soil is fully saturated, because either in the case of UU test or CU test or CD test, we said we will ensure that your soil is fully saturated. So when I say that we wanted to ensure that the soil is fully saturated, only on such kind of soils we are going to be conducting the test, then obvious that whatever might be the increment in pore water pressure that you have applied, whatever might be the increment in your confining pressure that you have applied on the soil sample without allowing any drainage. So automatically the increment in pore water pressure in the soil sample is nothing but it is equal to your applied deviatoric stress, which earlier also we have talked about. When there is no drainage allowed, and if you are trying to apply the loading which is uniform in all the directions on the soil sample, so increment in pore water pressure is nothing but it is equal to your applied confining pressure. That is what we even see in this particular expression or in this particular representation. Already residual pore water pressure was existing in your soil sample, and increment in pore water pressure because of the applied confining pressure is what otherwise I can also call it as your applied confining stress only, because your soil which is said to be 100% saturated, your B parameter is equal to 1. If you can just recall what we have said a couple of minutes earlier, we said that delta U That's the increment in pore water pressure because of the applied cell pressure is nothing but, we said it is nothing but which is equal to B into delta sigma C. If the soil is 100% saturated, this B parameter is equal to 1. And that's how we can say the increment in pore water pressure because of the applied confining stress is nothing but it is equal to your applied confining stress only. And automatically now I can go on to calculate your effective stress, because total stress acting on the soil sample is known. How much is the pore water pressures that are building up in the soil sample are known. So effective stress, if I go on to calculate, I do understand that your effective stress is nothing but total stress minus pore water pressure. So what we see is that this sigma C is getting cancelled, and automatically what we'll have is only UR. What does this UR indicates? UR indicates it is your effective stress, whatever is existing in the soil sample, which is same as that of your initial state, even before applying your hydrostatic pressure. That is your before the application of cell pressure. Whatever was the effective stress that was getting developed in your soil sample, same amount of effective stress is also existing in the soil sample, though your soil is subjected to your an all-round pressure, which is called as cell pressure. And in the next stage of loading, what we are trying to do is we try to increase the loading on the soil sample by applying only the loading in the vertical direction, which we are calling it as your deviatoric stress. So because of that applied deviatoric stress, there is an additional increment in pore water pressure is what we are going to be coming across with. Okay. So because of that additional increment in pore water pressure, obvious that the pore water pressures which are getting developed in the soil sample would further increase, and that further increase I can represent in terms of positive increase, or I can try to represent in terms of your negative increase. When do I come across with positive increase? You can see the symbols used here, plus or minus. So positive increase in pore water pressure comes into picture when the soil is normally consolidated or loose sand. Okay. And negative term is what we are going to be coming across in the case the soil is over consolidated or dense sand. So according to that, we'll be using that respective term plus or minus. And once we know how much is that corresponding increment in pore water pressure coming into picture, then we can go on to calculate how much is the corresponding effective stress that gets developed in your soil sample. Effective stress is nothing but applied total stress minus the pore water pressure. So if we go on to calculate, we'll be getting the values something like this as represented in this state of stress on the soil sample, both in vertical as well as in the horizontal direction. Now with the failure of the soil sample, that's nothing but applied deviatoric stress. What we will be indicating now is called as your deviatoric stress at the failure of the soil sample, and the corresponding increment in pore water pressure only due to the applied deviatoric stress is also indicated in terms of the failure of the soil sample. And accordingly, we are representing your effective stress, what is existing on the soil sample, both in vertical direction and in the horizontal direction. And to be more specific, if we need to clearly understand what is the state of stress now acting on my soil sample in terms of total stress and in terms of the effective stress, look at in terms of the effective stress at the failure of the soil sample, both in vertical direction as well as in the horizontal direction. If we go on to understand, in the vertical direction, sigma C is getting cancelled. Even in the horizontal direction also, sigma C is getting cancelled. And what we certainly understand from the discussion is your effective state of stress, whenever you are talking with regard to the effective state of stress acting on the soil sample, the effective state of stress in the case of UU test is independent of your applied confining pressure. I repeat, irrespective of how much confining pressure you apply on the soil sample, it doesn't matter. What matters there is only how much is that increment in deviatoric stress which was causing the failure in your soil sample. Okay, so that increment in deviatoric stress, what was required to cause the failure in the soil sample, only matters. And there is no effect of applied confining pressure in terms of your effective stress, what is being reflected. Okay, so from this I can conclude that irrespective of how much confining pressure you apply on the soil sample, in terms of the effective state of stress, if I want to understand for the soil in the case of UU test, the effective state of stress for soil sample 1 or for soil sample 2 or for soil sample 3 which were subjected to different confining pressures, irrespective whether they were subjected to same confining pressure or different confining pressure, doesn't matter at all. The state of stress, ultimately what remains on the soil sample is going to be same, because the expression itself says the effective stress in the vertical direction, effective stress in the horizontal direction. The expression do not contain the term of your applied confining pressure. It means that expression is independent of your applied confining pressure. So automatically your Mohr circle, what you are going to be getting when you are trying to talk in terms of the effective state of stresses acting on the soil sample 1, 2, and 3. So those effective state of stresses on sample 1 or sample 2 or sample 3 are going to be same, because it is independent of your applied confining pressure. If it is dependent on applied confining pressure, obvious that as different confining pressures are getting applied, then automatically your effective stresses developed with respect to soil sample 1 are different, sample 2 are different, and sample 3 are different. But whereas in this case, your effective stresses, what you are trying to calculate, is independent of your applied confining pressure. So whether you talk about sample 1 or 2 or 3, so automatically in all the 3 samples, the resultant state of stress, what you will be getting on the soil sample in horizontal and vertical direction, comes out to be same. Same in the sense, ultimately, whether you plot the Mohr circle for sample 1 or sample 2 or sample 3, all those 3 Mohr circles will be overlapped with each other. The effective state of stress condition for which, if you are plotting the Mohr circles, all the Mohr circles will get overlapped with each other. In the sense, you will be seeing only single effective state of stress Mohr circle being visible. For that single Mohr circle, whatever you have plotted with respect to the effective state of stress, how do we define the failure plane? So we define the failure plane to be passing through your maximum shear stress, obviously. So it's going to be a horizontal failure plane, what we'll be defining in such case. Okay, so let's go ahead and understanding further. Mohr circle in terms of the effective stresses do not depend on the cell pressure. Therefore, we get only one Mohr circle in terms of the effective stress for different cell pressures or different confining pressures what the soil sample is subjected to. It doesn't matter how much confining pressure you have applied, but ultimately you get only one Mohr circle, because the effective state of stress corresponding to all the soil samples is coming out to be same. And in terms of the total stresses, if you are trying to talk about, in terms of the total stresses, the Mohr circles are going to be different, but the amount of deviatoric stress which was required to cause the shearing in between your soil grains in the complete undrained state, the amount of deviatoric stress required to cause the shearing in the soil sample 1 or soil sample 2 or soil sample 3 in terms of the total state of stresses, the amount of deviatoric stress is going to be same. Okay, sample 1, though it is subjected to, let's say 3 samples I have got. Sample 1 is subjected to an confining pressure of 0.5 kilopascal. Sample 2 subjected to a confining pressure of 1 kilopascal. Soil sample 3 is subjected to a confining pressure of, let's say, 1.5 kilopascal. Irrespective of how much confining pressures were applied on 3 soil samples, but in terms of the total stress, the amount of deviatoric stress additionally to be applied on the soil sample to cause the shearing in sample 1 or sample 2 or sample 3 would come out to be same. When I say that increment in deviatoric stress in the vertical direction for sample 1 or sample 2 or sample 3 is coming out to be same, then it means that your radius of the Mohr circles, what you are going to be plotting for considered total state of stress condition, those Mohr circles are going to be having the same radius. Same radius in the sense, same deviatoric stress was required to cause the shearing in the sample 1 and sample 2 and sample 3. Now, in case if you are trying to define your failure envelope, either in terms of your effective state of stress condition or in terms of your total state of stress condition, your failure envelope is going to be purely horizontal. Okay, and this failure plane is going to be purely horizontal only when your soil is said to be fully saturated. In case if the soil is not fully saturated, the failure envelope, you are not going to have it as purely horizontal. Rather, you will be having certain slope what will be made by your failure plane. So here in this case, the failure envelope is having is making a slope which is equal to 0. But in case if the soil is not fully saturated, So your failure envelope is not exactly horizontal. Rather, you will come across with a situation where the failure envelope, this part of the region of the failure envelope, if you see here, so it is going to be like this, indicating some slope is existing, and that slope is not obviously equal to 0. So that's what we understand as effect of degree of saturation on your failure plane. So if your degree of saturation is not exactly 100%, then your failure plane is not horizontal. In case if the soil is fully saturated, yes, your failure plane is going to be perfectly horizontal. So what are those practical applications where we come across to perform what is called as UU test on your clay soil? Okay, so same type of examples, but however, the condition at which those cases what we are looking at are getting changed. Okay, so it's a soft clay once again on which we are trying to construct an embankment. In case if the embankment what is constructed on the soft clay is a rapid construction in the sense embankment is constructed at really at a very faster rate on that particular soft clay. So water cannot get drained at all through that particular soil sample. So in such condition of the soil, if I need to know what are the shear strength parameters of such kind of soil deposit on which you have your construction rapidly happening, so the corresponding soil properties of that particular soft clay, if I want to determine, so I can take a soil sample from there in undisturbed state, and I can go on to conduct what is called as your UU test, and from that UU test, we get if the soil is fully saturated, obvious that your failure envelope is going to be horizontal, irrespective whether it is you are plotting your Mohr circle in terms of effective state of stress, or whether you are plotting your Mohr circle in terms of your total stress. Okay, failure plane is going to be horizontal, which indicates that your angle of shearing resistance is going to be 0, and you will have what is only called as your undrained cohesion value. Why I am calling it as that cohesion parameter as undrained cohesion? Because you are not allowing any drainage throughout the test. Okay, as the test is conducted relatively over a faster rate, so we don't see the water getting dissipated out of the soil sample, because either in the case of the first stage of loading or in the second stage of loading, the water is not allowed to get drained out of the soil sample. So as the water is not allowed to get drained out of the soil sample, for that particular case, if I need to know what are the shear strength parameters, then I can take that soil sample, I can perform what is called as a UU test on that soil sample, and I can determine the shear strength parameters. So the subsequent shear strength parameters, what we are getting from your UU test, are going to be indicated as CU and phi U. Okay, phi U refers to undrained angle of shearing resistance, and CU refers to that of undrained cohesion. So in the case of your soft clay on which you are taking up a rapid construction, either in the form of an embankment or either in the form of any other construction coming into picture. So your soft clay, what we are looking at, would be mostly existing in undrained state, because you don't have sufficient time for your soft clay to have the drainage process getting initiated. So subsequently, in such kind of soil where construction is happening relatively at a very faster rate, so soil would be mostly there in what is called as an undrained state. So in such case, if I need to know the shear strength parameters of such soft clay, you can take a soil sample from that field, go on to perform what is called as your UU test on the soil sample. Okay, that's how. Next, in the case of your large earth dam, what is constructed rapidly with no change in water content of your soft clay. So if you are going on to construct a large earthen dam, if you are looking at the core portion is generally constructed by means of what is called as your clay soil deposit. And if soft clay is used in the construction of your core part, so in such case, your consolidation could not happen as the construction took place relatively at a very faster rate. So automatically, your shear strength, whatever we are going to be looking at in that soft clay, would be determined based on your undrained shear strength parameters conditions of the soil. This is another example, like footing placed rapidly on clay deposit. Placed rapidly in the sense the construction of the footing and the construction of the superstructure, what is expected to be coming up there on a soft clay. The construction on the soft clay or on that particular clay deposit is taken up at a very faster rate. You are constructing your foundation and then your superstructure at a relatively faster rate. So automatically the soil which is there below your foundation would be mostly existing in your undrained state. Okay. So in that undrained state, if I want to know what is the shear strength parameters of the soil, then I have to conduct what is called as your UU test on the soil sample to get your undrained shear strength parameters. Okay. UU test simulates the short-term condition in the field, because if I want to understand how does the strength characteristics of the soil are getting changed, even in the earlier examples or in this example. So at in the initial period of time in the sense maybe in the starting months or maybe in the starting couple of years, you might be seeing mostly the soil to be in undrained state. But with increase in time, what we see is that as the time increases, the water, because of that applied stress on the soil sample, the excess pore water pressure slowly starts getting dissipated out of the soil sample. And after some sufficient amount of time, if I want to know what will be the strength of your soil, means the strength of the soil now would be different from the strength of the soil after some sufficient amount of time. Now, why is the strength of the soil getting changed over time? Because now the soil might be in undrained state because of the loading what is continuously getting applied. But however, with the increase in time, due to that load what was getting applied on the soil sample, your excess pore water pressure dissipation might have happened, and the condition of the soil there would be different from that of the original initial condition. Okay. So if I want to know in initial stages how much would be the strength of the soil, then I'll conduct what is called as UU test. In the final stage in the sense after some sufficient time where we ensure consolidation process is going to be completed in that soil. After that sufficient time, it means it's a long-term process. When I say it's a long-term process, obvious that the complete excess pore water pressure dissipation might have happened. So what kind of test I should perform to know the shear strength parameters of that particular soil in a long-term basis? So that's nothing but I should look after for what is called a CD test, because in long-term basis, complete drainage might have taken place from your soil, and if excess pore water pressure dissipation has happened from your soil, automatically the shear strength of the soil in the drained condition would be different from that of your undrained condition. In the case of undrained condition, the effective stresses developed in the soil would be lesser, and obvious that the strength of the soil is going to be lesser. Okay. So it depends on when and how you want to understand the characteristics of your soil. So depending on when and how you want to determine the characteristics of the soil, you will be performing that respective test in the lab to know your shear strength parameters of the soil, to determine what will be the subsequent strength of the soil. And then moving on, let's say for example, let me just try to understand how to determine your deformation modulus of the soil. Okay, so for that, let us look at some stress strain relationships. The corresponding stress which was responsible for causing the shearing in the soil sample is what I am trying to look at. Let's say it's the deviatoric stress which is responsible for causing the shearing in the soil sample. So for that corresponding strain, what was developed in the axial direction, that is in the vertical direction, how your deviatoric stresses getting developed in the soil sample are getting changed. So what we see earlier, I hope we have already seen this kind of typical curves. Okay, so this kind of curve will be coming across in the case of your normally consolidated clay soil, or maybe in the case of your loose sand deposit. This is a typical curve what you will be getting when you plot a graph between deviatoric stress versus your vertical strain. That's nothing but the axial strain. Now from this particular curve, or for this particular curve, if I want to understand what are the deformation, because from the stress strain curve, we can go on to determine what is called as your deformation modulus of the soil. In the case of soil, I will not be calling it as Young's modulus. I repeat, in the case of soil, I will not be calling it as Young's modulus, because the word Young's modulus, if you can recall, we said, how do we define Young's modulus from your Hooke's law? when stress is directly proportional to strain, that subsequent proportionality constant what we are using is what we call it as here E. Okay, which we call it as Young's modulus. But here I am not calling it as Young's modulus, rather in the case of soil, to be more specific and technical, we call it as deformation modulus. What does this word deformation modulus means? Because once the soil is subjected to loading and after it is subjected to some loading, and at any point of time if you start removing the load from the soil sample, you don't see that soil come back to its original shape. In the sense, original cross section, the soil will not be attaining at all. Okay, so that's the reason why that so-called E, which earlier in the case of other materials which you have called it as Young's modulus, when it comes to the case of soil, we call it as deformation modulus. Notation is same, we indicate it as E, okay, but to be specific, technically we call it as deformation modulus of the soil. Okay, now how do I determine the deformation modulus of the soil? So there are various approaches, various ways by which one can try to determine the deformation modulus. One is by drawing a tangent to the initial portion of your stress versus strain curve. Okay, so in the initial portion of the stress versus strain curve, if you are drawing a tangent and if you are determining the slope of this tangent drawn, then I can call it as your initial deformation modulus. Initial deformation modulus means in the initial portion of your stress versus strain curve, you are trying to draw a tangent, and that slope of the tangent is what you are calling it as your deformation modulus. And that deformation modulus, how you have got? By drawing a tangent in the initial portion of your stress versus strain curve. Likewise, it need not be for initial portion. Let's say, for example, I want to know what is the corresponding deformation modulus of the soil for some 5% strain induced in the soil, or maybe for some 10% strain induced in the soil, or maybe for some 20% strain induced in the soil. Let's say, for example, for 5% strain induced in the soil, that means that point could be somewhere here. My initial point is here. That 5% strain, what I am referring to, that point is here on the curve. So I'll just try to join these 2 points by means of a straight line. I'll be extending that straight line, and the slope of this line is what is more technically called as secant modulus. The earlier one, you might have called it as your tangent modulus. This is what we call it as your secant modulus. The term secant modulus is once again defining you what is called as your deformation modulus of the soil only, but for corresponding some strain. Okay, for a corresponding strain of 10%, if I want to determine my secant modulus, so that 10% strain point on the curve is meeting the curve at some point here, and from the initial portion, I'll try to join these 2 points to represent a straight line, and the slope of this straight line is what I am calling it as once again secant modulus. But this secant modulus is for 10% strain. Okay, earlier was for 5% strain in the soil, my corresponding secant modulus value of the soil. Okay, so that's how we go on to determine your deformation modulus values of the soil, and your deformation modulus of the soil value, that's the E value of the soil, is going to be higher in the case of your over consolidated or dense soils, because if you look at your stress versus strain curve, for less amount of strain itself, you get what is called as a peak stress data like this. Okay, so in the initial portion of the curve, if you are trying to draw a tangent, the slope of that tangent drawn is a steeper slope. So obvious that your E value, what you are going to be getting, is relatively clay. But whereas in the case of your what is called as normally consolidated clay or loose sand, your deformation modulus of the soil is relatively less. Obvious that because in the case of dense nature of the soil or over consolidated soil, the strength of the soil is relatively more or high, because it's stiff in nature or dense in nature, because of which the strength what we'll be getting is high when it is compared with respect to that of your normally consolidated soil or your loose sand deposit. Okay, so let's try to solve one problem. I'll just directly note down what is the data given in the problem. Okay, let's say this is problem 1. In this problem 1, we are asked to determine the shear strength in terms of the effective stress on a plane within a saturated soil mass at a point where the total normal stress getting applied on the soil sample is on that particular soil at a point is 200 kilopascal, and the amount of pore water pressure what was getting developed in your soil sample is 80 kilopascal. The effective shear strength parameters of that particular soil are given. Okay, let's say for example this might be your ground. Maybe we are trying to look at some soil element somewhere here, and it is said that the soil element is subjected to what is called as your total normal stress. And we are saying it is a saturated soil. It means that the water table might be somewhere above the position of the soil sample what I am looking at, and it said that your total normal stress what the soil sample is subjected to is 200 kilonewton per meter square, and the amount of pore water pressure what was getting developed in that soil sample is 80 kilonewton per meter square. And what is also additionally given to is the effective shear strength parameters of that particular soil. That means C dash and phi dash parameters are given. So C dash value of that soil is 16 kilonewton per meter square, and the phi dash value of the soil is given as 30 degrees. Okay, and now what I am required to determine is the effective shear strength parameter, effective shear strength of the soil. So I want to determine your effective shear strength of the soil. So effective stress or effective strength of the soil, if I just want to determine, so I can simply write it as tau. Either I write it as dash or tau simply at the failure of the soil sample. Both are one and same, because either you represent in terms of effective stress or in total stress, the shear strength what you are indicating is same. So what we write it is C dash plus sigma dash tan phi dash. Why I'm writing it as sigma dash? Because I'm trying to calculate the shear strength in terms of the effective stresses. Okay. So what is my C dash value? It is 16. Sigma dash is nothing but sigma minus u into tan 30 degrees. So sigma value is already known, u value is already known. It's a straightforward substitution of data into this particular problem. 16 plus sigma is 200 minus u is 80 into tan 30 degrees. That is your strength of the soil at its failure in terms of the effective stresses when you are trying to define. 85.23 kilonewton per meter square is going to be the strength of your soil in terms of the effective stresses whenever you are trying to calculate. Okay, we'll conclude for today, and in the next class we'll try to talk about the other lab tests, or maybe in foundation engineering course also we'll be trying to talk about that particular point, that is your vane shear test. Okay, so that we'll try to take up in the next class.